starting by example 1, here's problem 1 from the worksheet. In problem 1, just disprove the statement. If we have a statement here, if we have a statement, if A and B both are real numbers, then log of A times B equals log A plus log B. So we need to disprove this statement. Okay, so how to disprove this statement? To answer, so we need to have some info about such type of functions. Here we have log, which is the same as len, the same as len A times B. This equals to len A plus len B. Okay, where both A and B both belongs to a set of real numbers. So we need to negate this statement. We need to disprove this statement. How can we do that? Just to provide counter examples. In general, this statement is working for any real numbers on condition that these real numbers belongs to the domain of the len function. Len 2 times 3, this equals to len 2 plus len 3. Len 10 times, for example, 50, this equals to len 10 plus len 50. But this is not the case. Len has a problem with negative values. The domain for len in general have len x, for example, len x. So x have to be greater than 0. This is the form of the len function. Len have to be greater than 0. If we have a equals to negative 1, for example, a equals to negative 1 and b equals to negative 1, negative 2, another negative value, by the way, negative 2, for example. So this means that for the left hand side, len a times b equals to len negative 1 times negative 2. As we know, we proceed the product step, then affected by len. Negative 1 times negative 2 is 2. So len 2 gives some value, which belongs to a set of real numbers. Disregarding to the left hand side. What about the right hand side? Okay, actually in the right hand side we have two problems. The first problem is len A plus len B. What is len A? This len negative 1. What is len B? This len negative 2. Both does not belong to the domain for len. Here negative 1 does not belong to the domain for the len. The same here, this negative 2 does not belong to the domain for len. Okay, so we can consider in A equals to negative 1 and B equals to negative 2 are counter examples for this statement. Then A equals to negative 1, B equals to negative 2, negative 3, negative whatever are counter examples. Both are one counter example for this statement. Let's prove this statement. If you have n and this n belongs to this set contains 1, 2, 3, 4, 5. Then 3 divides 2n squared plus 1. Just substitute and find the counter example that negate this statement. Just substitute with this set at n equals to 1, at n equals to 2, at n equals to 3, and so on. For n equals to 1, for sure, we have 2n squared plus 1. This equals to 3, which equals to 3 times 1, some value which is divisible by 3. But what about n equals to 2? For n equals to 2, 2n squared plus 1 here equals to 2 times 4. This is 8 plus 1 is 9, which is 3 times 3. For n equals to 3, 2n squared plus 1, this equals to 3 power 2. 3 power 2 is 9. 9 times 2 is 18 plus 1 is 19, and 19 can't be written as 3 times k. So n equals to 3 is a counter example for this statement. In problem 3, disprove the statement for every two positive integers a and b, a plus b power 3 equals to a power 3 plus 2a squared b plus 2ab plus 2ab squared plus b power 3. So we need to provide the counter examples for a and b that negate this statement. I think that we can try with any values. Already you know that the expansion for a plus b power 3, a plus b power 3, this equals to a. This equals to the first cube plus 3, first square times second plus 3, first times second square plus b power 3. So just defining such form for the perfect cube like this one. So this wrong, by the way. Then just substituting with any values, I think it's working to negate this statement. If a equals to 1, for example, b equals to 2. So now go to find the left and right hand sides. The left hand side is 1 plus 2, this 1 plus 2 power 3. 1 plus 2 is 3 power 3, this is 27. This is for the left hand side. What about the right hand side? I'm just guessing that in A and B will break this statement, will disprove this statement. So I'm trying. Maybe it's working, maybe not. If it's not working, so I'll try with another element and so on. So what about the right hand side? The right hand side is a power 3 plus 2a squared times b plus 2a times b plus 2ab squared plus b power 3. Okay, so a is 1 plus a squared times b. Here it's 2 times 2, this is 4, plus 2 times a times b, this is 4, 2 plus 2 times a times b squared, this is 8. As in here, b power 2, it's 2 power 2. 2 power 2, this is 4, 4 times 2, this is 8, plus b power 3, this is 8, 2. This equals to 16 plus 4, it's 20, 20 plus 5, this is 25. This is the right hand side, this is the left hand side. So 4a equals to 1 and b equals to 2. The left hand side does not equal to the right hand side, which means that in this is considered as a counter example for this statement. This is the worksheet problems, by the way. Disprove the statement. Here, just disprove the statement. For every positive integer n, for every positive integer x, and for every integer n is greater than or equal to 0, and for every integer n is greater than or equal to 2, the equation x to the power n plus x plus 1 to the power n equals to x plus 2 to the power n has no solution. So we need to think about that. For every x, where this x is positive integer, and n is greater than or equal to 2, this equation has no solution. We need values for x and n satisfy this equation. The statement is in this equation has no solution. So we need to negate this statement. To negate this statement, we need to find values for x and n that has solution. Okay, so can you try with values that satisfy this equation? Can you try with values that satisfy this equation for x and n? X equal 1 مثلا, x and n equals 2, x equals 2, x equals to 3. Let's try with x equals to 3 at x equals to 3, and for example n equals to 2. Think about the left and right hand side. The left hand side equals to x power n plus x plus 1 to the power n. This equals to 3 power 2 plus this 4 power 2. 3 power 2 is 9, 4 power 2 16. This equals 2 to 25. This for the left hand side. What about the right hand side? It's x plus 2 to the power n. X is 3. So x is 3. 3 plus 2 is 5 to the power 2. This equals to 25. So this means that in x equals to 3 and n equals 2 is a counter example for this statement. Disprove this statement if n1, n2, and n3, these are 3 distinct positive integers, different positive integers. Then 3 divides 2 to the power n plus 2 to the power n1 plus 2 to the power n2 plus 2 to the power n3. We need to negate this statement. How can we do that? Just try by assuming any values for n1 and n2 and n3 on condition that in n1, 2, and 3 they are distinct values, distinct positive integers, and verify that in the resulting value is not a multiple of 3. So start by at n equals to 1, n equals to 2, and n equals to 3. So substitute 2 to the power 1 plus 2 to the power 2 plus 2 to the power 3. It's 2 plus 4 plus 2 to the power 3 is 8, which is 6 plus 8. 6 plus 8 is 14, which is not divisible by 3. So n equals 1, n1 equals 1, n2 equals 2, n3 equals to 3 is considered as a counterexample, which is training on how to provide counterexamples. Given a statement and we need to disprove the statement, so just to provide a counterexample. The second part of the lecture is disprove the existence statement. Okay, already we know that if we would like to negate there exists statement, there exists x belongs to R on condition that b of x is equivalent to the negation of there exists is for every x belongs to R on condition that the negation of the b of x. In these exercises, it's requested to negate there exists statements. Disprove the statement. There is an odd integer n such that on condition that n squared plus 2n plus 3 is odd. Don't forget that in the last lecture we mentioned that in case of the disproof, as we have two types of statements for every and there exists. For every, its negation is just there exists. There exists, its negation is for every. Okay, so we need to work with this chart. There exists an odd integer on condition that n squared plus 2n plus 3 is odd. So here there exists statement. There exists statement. We need to negate it, so we need to prove. Okay, what to do? Let n is an odd integer. N is 2k plus 1. This is the form of any odd integer. And then substitute with this n here to prove that n is not odd, this is even. So n squared plus 2n plus 3 will be 2k plus 1 square plus 2 times 2k plus 1 plus plus 3. Then just expand. You will get the first squared, 4k squared. First times second times 2, this 4k plus the second square plus 1. Plus here, this 4k plus 2 plus 3. Now we have 1 plus 2 plus 3, this 6. This regarding to the constant. 4k squared is the first term. Regarding the linear terms, we have 4k plus 4k, 4k plus 4k is 8k. So now we have 4k squared plus 8k plus 6. The question now, can you factor 2? Is it even or odd to determine if this is even or odd? So the question is, can you factor 2? Sure, we can factor 2. Here, this will be 2k squared plus 4k plus 3, which is even, not odd, as mentioned in the statement. So this is the way for disproving such form of statements. If the statement is there exists statement, so you have to prove in this statement there is a real number x on condition that in x power 6 plus 2x power 4 plus x squared plus 2 equal to 0. The question is, negate the statement that in this equation has a real solution. Type. Think about this equation, x squared plus 2 equal to 0 for every x belongs to R. X squared plus 2 equal to 0 has a solution. Can you try negating this statement? Start by this one. Can you try negating this statement? X squared plus 2 has a solution. We need to negate this statement. How come? X squared plus 2 equal to 0. From calculus 1, we know that in x squared, for sure, greater than or even equal to 0, right? So this means that in x squared plus 2, I'll add 2 for both sides. By adding 2 for both sides, so x squared plus 2 is greater than or equal 0 plus 2, which is 2. So this means that there is no values that makes x squared plus 2 equal to 0. This is the proof, by the way. Okay, so I'll do the same here for this equation. Here we have x power 6 plus 2x power 4 plus x squared plus 2. This equation has a solution? No, this equation has no solution. Okay, prove that. Already x power 6, x with even power. So x power 6 is greater than or equal to 0, right? What about x power 4? X power 4, 2 is greater than or equal to 0. What about x power 2? X power 2 is greater than or equal to a or equal to 0, which means that regarding the first three terms, x power 6 plus x power 4 plus x power 2 These three terms are greater than or equal to 0. But what if we would like to add 2? To add 2, so x power 6 plus x power 4 plus x power 2 plus 2 is greater than or equal to 2, which means that the left-hand side cannot be 0 for any values of x, which means that this equation has no solution. That's it. Okay, disprove this statement. There is an integer n such that n power 3 minus n plus 1 is even. So we need to disprove this statement. How can we do that? Take care that there is an integer n to disprove, and there exists is equivalent to for every. Okay, for every. And this n, he mentioned that there exists an integer n. It's open statement, an integer n. Okay, an integer n, so we need to prove for n is even, as we identified before. If we mention that and we have n integer, so we need to provide our proof for n is even and n is odd. So you will provide your proof for both cases if n is even. N is even means that n equals to 2k. So just substitute in this statement. So n power 3 minus n plus 1 will be, substitute with n, 2k power 3, this 8k power 3 minus 2k plus 1, which is odd. We factor 2 times 4k power 3 minus k plus 1, this is odd. This for n is even. If n is odd, you will do the same, but for n equals to 2k plus 1, n equals to k plus 1. Substitute then n power 3 minus n plus 1. This will be 2k plus 1 power 3 minus 2k plus 1 plus 1. Okay, expand the perfect cube will be the first cube, which is 8k power 3. First square times second times 3. First square is 4k squared times 3, it's 12k squared. First times second square times 3, it's 6k plus 1 minus 2k minus 1 plus 1. 1 minus 1. So the resulting expression will be, already here we have 1. 6k minus 2k, this is 4k. So the resulting expression will be 8k power 3 plus 12k squared plus 4k plus 1. Is it even or odd? We can factor 2. It's 4k power 3 plus 6k squared plus 2k plus 1, which is odd. Okay, so this is the case if we need to disprove a statement starting with there exists. Okay, this was the second part of the lecture. Now I'm going to the third part of the lecture, which is the proof by contradiction. Now going to the proof by contradiction. طيب, what is the meaning of the proof by contradiction? Actually, for some types of proofs, for some types of statements, we can't prove the statement using any of the traditional techniques that we studied before, like the direct, contrapositive, vacuous, or even trivial. So we use this technique, which is the proof by contradiction. How it's working? Actually, we have some steps. We have for every x belongs to some set, we need to prove b of x. So the first step in this technique, assume the contrary of this statement, of the given statement, the contrary of the statement. Assume the contrary of the statement p of x. This step 1. Here step 2. Okay, so in step 2, I'll try to prove a confusion. I'll try to prove there exists some sort of confusion, some sort of contradiction in this statement, some sort of conflict between the assumption and what I need to prove. Confusion, contradiction, conflict, something like this. So as I reach it to this point, of the conflict or of the contradiction or of the confusion, this proves the truthness of the original statement. What's the meaning of the original statement? The statement without the contrary. The statement before the contrary. Let's start by this example. Example 8 in the lecture. There is no smallest positive real number. There is no smallest positive real number. We need to prove this statement. So what to do? Assume to the contrary that there is a smallest positive real number. You have to write down these statements. You have to provide this in your answer. There is a smallest positive real number. This step 1. Write down this as, say, R. Okay, so since we have R divided 2, this R divided 2 for sure is less than R, and at the same number it's greater than 0, isn't it positive? Then this follow that in R divided 2 is a positive real number smaller than the smallest positive real number that we claimed at the beginning, smaller than R. This is a contradiction. As in this a contradiction, so this means that in the original statement without contrary is right. So this proves this statement, and this means that in this statement is wrong. In example 9 here, no odd integer that can be expressed as a sum of 3 even integers. No odd that can be expressed as a sum of 3 even integers. So assume to the contrary. To prove the statement, assume to the contrary. Assume the contrary. Sum of 3 even integers. Now we have 3 even integers. There exist x, y, and z are 3 even integers, where x equals to 2m, for example, y equals to n, and z equals to 2k, 2l, أي حاجة. So sum x plus y plus z, x plus y plus z will be 2 times, where you have to write down that in n, m, and l belongs to set of integers. So x plus y plus z is 2m plus n plus l, which is even. Thus, this is a contradiction. This means that in this statement, the contrary is wrong, and this one is the right one. This proves this one. Good. So now we need to prove that the sum of rational and an irrational number is irrational, not rational. So how to do? Assuming that assume to the contrary that. Assume, and you have to mention to the contrary. Assuming to the contrary that there exists a rational number x and an irrational number y, their sum is z. So we have rational here, sum of rationals, and irrational is irrational. So we have here x plus y equals to z. He's claiming that in x, which is rational, plus y, which is irrational, equals to z, which is rational too. Okay, so their sum is z. Since x is rational, so we can write this x as a divided b, for example, a divided b. The same, he claimed that in z is rational, so z can be written as, for example, c over d. X plus y equals to z, since in x plus y equals to z, which means that in y equals to z minus x. So y equals to z, which is c divided d, minus x, which is a divided b. Okay, common denominator, it's bd. In the numerator, it will be cb minus ad, which means that in this y is written in rational form. It's contrary, or it's a confusion with what is mentioned at the beginning, that in this y is irrational. So you will mention that in this is a contradiction. So as in this contradiction, this means that in this statement to the contrary, there exists a rational number x and an irrational number y, and their sum is z, which is rational, is z rational. So this claiming is wrong, and the statement is the true one. So example 12 in the lecture, it's requested to prove that in the real number root 2 is irrational. Okay, so we'll assume to the contrary using the proof by contradiction. Assume to the contrary, root 2 is rational. So root 2 is rational means that root 2 can be represented as a divided b, where b does not equal to 0. Both a and b belongs to set of integers. And a very important condition that in a divided b in the simplest form. Okay, so from this step, as in we have root 2 equals to a divided b, then we mean that we can represent a equals to root 2 times b. And by squaring both sides, so a square equals to 2b square. A square equals to b squared and b squared is integer, then a square is even. And we already proved that if a square is even, a is even too. And you have to provide a proof. If a square is even, then a is even. You have to provide this proof. Okay. So now a is even. This means that we can rewrite a in the form 2, for example, 2l. And the back substitution here, a square would be 4l square. After substitution with 2l, it would be 4l squared. This equals 2b square. Simplify this, divide by 2 for both sides. So 2l square equals to b square. Then b square is even. And from it, we can conclude that b is even too. B square is even, then b is even. So b can be written as 2k. And substitute. Now we have two important points. B equals to 2k and a equals to 2l, which means that a divided b is not the simplest form. So this means that in root 2 cannot be represented as a divided b, which means that in root 2 is not rational, or in other form, root 2 is irrational.